for joining us for the next installment of our speaker series. Today, we will hear a presentation from Dr. Vijaya Rangari. Dr. Vangari is a professor at Tuskegee University in the Material Science Department and the Material Science and Engineering Department. He has secured over $15 million in funding as a principal investigator and over $50 million as a co-principal investigator or participant. He has published more than 250 research articles in peer-reviewed journals, conference proceedings, and 25 chapter books. He has 3 patents and has presented over 50 invited talks at national and international conferences and research institutions. Without further ado, Dr. Rangari.
Thank you, Nana. I think thank you very much for your kind introduction, and I'm happy to share some of our results, what we have been working on this plasma synthesis, modification, and some of the sustainable carbon from the waste resources. As Dana said, I'm part of the Alabama EPS and professor in Material Science and Engineering Department at Tuskegee University. And you can get more information on this Google link for the journal publications or other things, or if you need to contact and this email, you can contact me and try to get back to you. Okay, so here, this is some of the research fields. We have been working on it from several years, and these are the current research work going on. And you can see that we have several research fields. Most of them are related to the either we have a synthesis and characterization of varieties of nanomaterials. Some of these waste materials, like we have a CREST Center. This is a $5 million 5-year grant. This is a Center for Sustainable Lightweight Materials, and we have other several NSF grants, and also we have a PREM. This is funded a few years back. This is a partnership for the research and education in multiferrite polymer composites. And also I'm part of the EPS, Alabama EPS. This is where I'm going to talk about the kind of work we are doing in polymer composites. And we have other research grants also. So to say here, the one we are talking today about this plasma science and how the plasma is used for the materials applications, especially polymeric materials or even a nanoparticles or nanomaterials. So if you can look at it in the literature, a lot has been done, but it's not very specifically tuned to the nanomaterials like a powdered samples. It's very recent ones. People have been trying to modify the powders by using the plasma. So on the powders and also the plastic materials. So some of these plastic materials are very toxic, and the processing or modifying or making new is slightly difficult task. So we are trying to look at this using this plasma to make polymers more marketable, in the sense where we can use for the compatibility or a hydrophobic or hydrophilic nature, or sometimes even make it much harder cross-link polymeric materials by simple plasma treatment in various surface modifications. So that's what I'm going to share some of the results what we are discussing. Here, we all know that here the global economical means ecological problems, where we have the energy crisis, the development of new materials always is a tricky part of it, and polymeric materials are becoming more and more varieties and trying to get rid of them. So in the sense, some of these applications, what we are using it instead of making a new one, and whatever is existed in the commercially or even in the waste materials, once we use it, lifetime is over, then we have to reuse those polymers for the better applications. So that's where in the main focus of this work, what we have been doing on here. So synthesizing is slightly difficult, but we can easily modify or change the surfaces for useful application. That's what we are trying to do it in this case. So the main important aspect of this, most of these kind of polymeric materials, the pre-treatment or a post-treatment, in the sense the polymeric synthesis is made, we can treat the polymers and make it to the different varieties of applications. For example, if you want to make some of these polymers are hydrophilic, and some of them are highly hydrophobic, and for some applications we have to change them. And some of them are hydrophobic polymers. The mechanical and other properties may be very good, but if it is hydrophobic, it may not be useful for hydrophilic applications. And similarly, Hydrophilic nature, if they have it, they might be very good, but we cannot be used for the hydrophobic applications. Even biomedical applications, sometimes we need the hydrophobic nature where we are really using this kind of application. So there are several other applications like increasing the hardness and adhesion, and anti-fouling is a big problem here in the boat industries and the marine industries looking for this anti-fouling or anti-fogging, some of these lubricant, biocompatibility, and all those kind of applications. So these are the things can be easily changed with the using the simple plasma treatment. So that's what we are going to talk about it. So what is plasma? It is all, we all know that it is a fourth state of matter that exists in the form of electrons, protons, and charged particles will be existed. So ion, the gases are electrified with these extra electrons. So that's where you're going to modify some of these surfaces. And this to make these kind of things, and generally solid materials it's much easier because we have a vacuum, and then you can create the plasma and can expose it, but the hard particles are much better solids one. But in the case of other materials like a powdered sample and all those things, it's like it will be tricky because we have a vacuum and we have to touch with the vacuum and powder going to suck it into the vacuum. So those are the things, some of these difficulties we had initially. So we come up with a solution working with this company, and they custom build this reactor here, the plasma. You can see that plasma can build up in the chamber, and also there is a rotating drum, and that drum can we can put the powder samples or even pellet samples, whatever we want, we can. And the drum rotates at the same time, the plasma created and it will expose to the particles inside the powder. So that's where it is, and the powder is not sucked into the vacuums. The design is such a way that it cannot escape. And it will also we have some toxic gases like a fluorine or other gases if you want to use it, ammonia, fluorine, those kind of things. For this, we have a scrubber so that you can get the toxic gases in the lab. So to do that, and here, these plasma, as we mentioned here, we have a surface on the any substrate, or you have any particles or a powder, and you can do a lot of chemistry here. In the sense, basically, the reactive gases when we have like a fluorine, or like for example, SF6, if you take it, and you can fluorine is going to interact with the sample, and you can chlorination can be done. That's a much easier process. I can show you some of those results, and also the any other, for example, if you use an ammonia, that can be possible to use it. Even oxide or oxygen plasma can be created, and surface cleaning or surface modification on the particles can be done. So these are the some of the simple procedures we can work with, and we can modify several types of polymers, not only any one or two polymers, any polymer we have. This is the starting from this high engineering applications of the polymers like polyamide, polyester, polycaprolactone, you name it, all of them. And also some of these regular polymers like polyethylene, polypropylene, where we have like a trash bag, and like even the waste water bottles, this kind of things is like a lifetime of water bottle is only a few minutes. When you drink in the water, in the bottle is waste. And those kind of polymeric are, you can see that all over. And we're trying to get rid of them and then try to reuse and repurpose them for useful application. Those are the things, and also there are other biodegradable or bioplastics are using for biomedical applications, or some of these plant-based polymeric materials, which we naturally they are hydrophilic, so we try to make them to hydrophobic to useful applications. So these are the some of these applications we can play around with these using plasma to make all these kind of changes here. And composite materials, of course, we can pre-treat or post-treatment can be done to change the modification. So this is one of the simple example here to show you here. This one we did it like a polycaprolactone is a simple biocompatible polymer, and it is a hydrophilic nature. So we need to make it slightly hydrophobic for some of these biomedical applications. So this is a very simple procedure in the sense this polymer, polycaprolactone is FDA approved biocompatible polymer, can be used for the biomedical applications or tissue engineering applications, and highly hydrophobic and poor cell adhesion, this kind of thing, and also plasma treatment already being used to surface modification, and this is be affecting the mechanical thermal properties and crystalline nature can be altered. So by using this plasma treatment, and without the plasma treatment, the contact angle, and with plasma treatment contact angle, we can alter it. So we can change either way, whatever way we want it, so that for useful application can be used. And these are some of the results. We can see that oxygen plasma, we used it to make it to the make a treatment surface of the simple polycaprolactone pellet. And we can use the neat polymer contact angle is 67. And we treated the plasma oxygen plasma treatment for several minutes, like 5 minutes, 10 minutes, 20 minutes, and you can change the oxidation of the contact angle, we can vary. So the contact angle varying is very basic principle. You can show that is the hydrophilic or hydrophobic nature of the material. So we can clearly see that a simple 5 minute, 10 minute treatment, you can change the properties of the polymer, either way, whatever way we want it. It depends on the kind of gas or type of pellets and all those things. And this is a simple the plasma treatment where we have this RF plasma 150 watts, and duration we use 10, 25, 10, 15 minutes, but we can use maximum time, whatever time we want it, we can use it. There is no limit how long we can proceed, how long we can expose to this one. And this is a generally, this one paper is published in JOM in 2020, and we have characterized and published and shown everything how the plasma treatment will help modifying the polymeric pellets. And the other important things are we are looking at the other materials. We work a lot in this other type of nanoparticles, biocompatible or those kind of materials, and most of them are agriculture waste material, like a peanut shell or coconut shell, rice husk. These are all these agriculture waste. Once the main important ingredient is gone out, then you will have it. These are the waste will be plenty, and people try to get rid of them because it's very difficult to takes more time to disintegrate. And also there are some other like the chicken egg shells, calcium carbonate, or packaging waste, or bone ash, you name it, all these seashells, all of them are basically some kind of a waste, agriculture waste or poultry waste, these kind of materials. And all of them are useful for some applications if we have a right surface for the compatibility, where we are using for polymer composite or electronic applications or battery applications or those kind of things. Even cellulose, from the plant-based cellulose is mostly hydrophilic, but we can make hydrophobic 5-10 minutes treatment, and we can use it for the polymer composite. And the end of the life, we can easily biodegradable and can put it in the soil, it will degrade, there's no toxic and other kind of stuff. So we can use this kind of treatment here. So I share some of those results, what we are working on it. And one of them is sugarcane bagasse. Sugar cane, and in the plenty is available. Once if the sugar is juice is extracted, and this on the bagasse what we have, that much is the waste material, and try to burn it, and that is again the carbon pollution it comes out. But if we can use for different applications, we can use for the advanced engineering applications. So for that reason, you can see that carbon is extensively studied. Actually, if you have known in a few years back, like 10 years back, carbon fluorination with a simple plasma, it would have been a big thing, because we used to have these carbon nanotubes or graphene sheets and any other carbon material. We used to chemically modify the fluorination. That's a tedious process. And also we used to use all toxic gases and other kind of stuff. But this is a very simple process. We can modify the surface of the carbon, and we can attach to the fluorine to the carbon, and is much easier and is compatible for the most of the epoxy or thermoplastic polymeric material. So that's the reason we can show the carbon is very important material. So I'm going to show you some of those the precursors where we can make this carbon. And this is the way where we are sustainable carbon, in the sense we producing this carbon from the waste resources, as I showed you earlier, rice husk and coconut shell powder or packaging waste or even the cellulose waste, those kind of things. They are abundantly available in the nature, and most of them are waste material. As you can see that some of them you can listed here, coffee grind, for example. Coffee grind is once you extract the coffee, and then the waste material will be there, plenty will be put into the landfill. So that coffee grind has a huge amount of nitrogen infused in the carbon. So that carbon can be used and you make it highly porous, and then you can use for the some filtration or any other engineering applications. There are so many applications. You can see that here, soybean, and also the softwood, sawdust, rice husk, coconut shell, wool, and you name it, several of them. So again, this is again I'm talking about the coconut, rice husk. As I mentioned here, rice husk is plenty available. As I mentioned, around 140 million tons of rice husk is generated annually. Then is once the rice is extracted and the hull, whatever we have, that has a huge amount of carbon and silica. So that can be extracted. You can see that we have the cellulose is 35% and the rice has cellulose 35% and also lignin and silica is 13%. So these all can be into carbon and silica can be extracted also separately. So we have been working on that, and that's another talk. But here, this again, the packaging waste. You all know that when you get a small amount of any chemical material, like aldrich or any even sometimes small chemical things, you get like a 1 gram material, but you have a 10 kg of packing on those kind of material. So this packaging material is mostly made of even waste bio-based material or even synthetic polymeric material, but it's a waste. So we have to recycle, we extracted it and do for some useful application. So this is one of them we have published. I'm going to show some of those results where we can get this one from this. You can get the nice carbon, useful carbon. Anything you burn, you get a carbon, but it's not useful because they are very big and particle sizes are not useful. But in this case, and we can get this nice carbon, then can be used for the polymer applications. And another important application here, another source of carbon is chicken feathers. You can see that the chicken, we all know that whenever we have a chicken, the birds are useful, but once the chicken is extracted, then the feathers are waste material. So there's a plenty of feather waste is available. Some of them are using small amount for some applications, but mostly it goes waste. So we have been working on this one to get this carbon and also the keratin, and another important biomaterial available in the chicken feathers as a keratin. So we get these two materials for biomedical applications. Keratin can be used, and also this can be the carbon extracted can be used for the carbon application. All these carbons have a different applications, and also they have different since they have a different source, the final product of carbon is also different. Like you have surface area different, and also some of these properties are different from the source of different carbon, the way they have formed in this. So these are the materials we can get. Like for example, as I mentioned here, the keratin is 92%, the huge amount of keratin in the chicken feathers. So can be converted into carbon or can be used for the other biomedical applications. And another source, as I mentioned here, is coconut shell powder. We are all aware of it. Plenty of coconut shells are available throughout the worldwide. Then that's a waste material, but can be used. A huge amount of coconut shell contains cellulose. We have hemicellulose and also the other solvents, and also we have a huge amount of the carbon sources. So we can use for the carbon. We can almost like a 50% of carbon we can extract from the sources when we burn it right. So how do we do this one here? In this case, we are using this special reactor here. This reactor is a specially designed, actually, can high temperature pressure reactor. So this reactor can go 1000 degrees C, and also we can apply the pressure around 200 psi pressure we can apply externally. So that gives a very good enclosed environment to heat it at high temperature and the pressure. So the most of the times you may not end up having external pressure. We can use the pressure whatever is created while burning it. For example, if we take a rice husk, we have a lot of carbon material and also the hydrocarbons are there. When you burn it, you are getting the lot of the pressure buildup itself within the reaction itself. It creates the pressure. So that pressure it can be used as the pressure. Sometimes that we call it as an autogenic pressure. When you create that pressure can be used in the reaction itself. So instead of expelling outside and getting into the environment pollution, we can keep it inside and we can use it for the reaction so that we can at lower temperature we can get a very good product. So this is the main reactor. We use it and we can control the temperature and pressure, whatnot we can do and monitor every bit of it. And this is the one we use it for this kind of reactions here. We can burn it at least 10 grams. So this is 100 grams capacity of the material. We can use it maximum, but generally for the lab scale, we use it for like a 10 grams maximum. Any of them, we burn it and carbonize them. And that's the uniqueness of the carbon. Instead of burning open or burning in the tube furnace, we may not have the same effect. That's what I wanted to stress here. So we get this reaction, the carbon, and then can be used for the different applications. So this is one of them where we have the carbon silica where we get the rice husk one. I can see that the rice husk we burn the similar way I showed you earlier. We get the husk, is plenty is available. Actually, one of this company in US, we call them and they send us the free material, and we can carbonize them, and we can give the rice husk as a 60% yield you get. When you paralyze them, then you have a 52% of carbon and 48% of silica. It's almost 50% of both the materials. It's a very unique material. We can get silica and carbon, both of them together here, and we can also separate them. So we have another procedure in, but in this case, we are using as a filler material. So both of them are useful. So we use it as it is, what we are getting it from the this kind of sources. So here, this again, I don't want to bore you here. We get this, all this analysis, we'll do it, X-ray diffraction and also surface area measurement and all those kind of things to make sure that what we are saying is exactly right kind of carbon, and we are getting other silica material. This is one of them, is a silica, crystalline crystallite silica you get, especially from the rice husk. That's a very nice, highly crystalline silica you can produce from the rice husk. So then we use the plasma treatment here. This is the one actually we published in Journal of Materials later in 2021 this year. Again, the powder will be taken and we can use this same reactor I showed you earlier. I know we can use the different gases. We can use the SF6 or oxygen or nitrogen. Any gas can be, one is a carrier gas and another one is the reactive gas. So both of them can be used in the reaction to expose the material. So we have the rice husk derived. This is 100 degrees, 1000 degrees heating, and then we have a SF6 we use for the fluorination. So the fluorine is very important material in the sense it can be biocompatible with many of the epoxy or thermoplastic polymeric systems. So that's the reason we try to see whether we can modify the surface. We can clearly see that this is very clearly shown you that this modification can easily done when we use this silica, the carbon what you get it, and we treat it at different timings, you get the surface modified, etching, and you get the highly porous material. You can, again, it's easy to understand from the XPS analysis, and we treated with argon and oxygen and SF6 and all the three, and we can clearly see that when the rice husk treated here, the data you can clearly see how this oxygen content and carbon content varies, and at the same time the fluorine content varies. When we treated with the fluorine, you can see the 14% fluorine is available in the carbon. So that's a huge amount of the fluorine we can get the compatibility of the epoxy or other systems. And also sometimes even simple oxygen, it also changes the oxygen content in the sample. Then that will also be good for some of these polymer composite preparations or a filler material. Even simple argon, it does it. So any of these treatments can be easily done, and then we can simply characterize, and you can see that where we have the fluorine, other variations can be varied by different timings. So what kind of timing and the flow of the gas, we can alter the flow of the gas. You get a different gas kind of things you can pulse with. So these analysis, these treatments can be done. As we mentioned here, currently we have the system, we can treat argon, oxygen, SF6, and also ammonia. These are the 4 things we can do it in the lab with the setup we have. And again, with this another one, the work we are talking about this waste plastic material, the plenty is available like a water bottle, Coke bottles, and all those things. You can see these images everywhere in the net. These are the things are waste materials end up in the sea, or any other environment. Environmental pollution is huge with this kind of plastic. So what we try to do it is here, one of these PET bottles, we took this one PET bottle, a very small amount is recycled, still plenty is end up in the sea and all the landfills. So those are the things we can try to use for the useful applications here. So what we have the same, I showed you earlier, the reaction we did it here with the high temperature pressure reactor, and we get the carbon, and that carbon, what we did is that carbon you take it and modify, or you can use this slightly the same carbon and the PET, the waste material, crush into the polymeric material, make a filament, and you can make a 3D printed component. A 3D printed component can be used for automotive applications or any some small components can be 3D printed for useful applications. So generally, this one can be automotive or other things. So these materials can be once you extract, and we again characterize and shown you that how this carbon can be used for the any applications here. And we do the surface analysis, surface area measurement before simple carbon and after treatment, and how we can get the different kinds of carbons here. And you can see the surface modification of the carbon, but the different treatment you get different porosity, and that makes it more compatible with the polymeric materials where you can get this kind of application. So this is again some PM to show that how porosity is there in the nanometer scale level. There is a highly porous, and also there is a crystallinity of this material. That's where useful for the polymeric composite application. And again, we did some of this mechanical testing to see how these polymeric materials with infusion of carbon, the properties change. And we can see that the huge change in the properties where we have this is a neat carbon and the strength. This is a simple tensile strength. There is a pulling the material tensile strength. This shows that drastic increment by adding the small percentage of carbon, 1 to 10%. That's a huge amount, and instead of getting rid of the waste material from the environment and useful for the any recycling materials for this kind of application. This can be again actually post treatment also can be when plasma can be treated to make cross linking and making higher strength, and that's the work is going on here. Still we are not we don't have slides here, but that's the work is in continuation. So to show you that the strength increasing in the neat polymer and we're adding the different carbon, you can see that increment is huge. So that's a drastic increment in the adding small amount of 1 to 10% of carbon, you get a significant increment. This is the material where we have, I think this one is published in ACS Sustainable Materials, I think 2 years back. This work we can get the more information on that if needed. And again, this is one of them. We plasma treat it, the same carbon when we polymer fill it. And again, this one is a plasma treatment. The one we did it, again, this is a SF6. The fluorine is very good for the carbon. Carbon surface modification is slightly difficult. If you know the chemistry from the other sources, it's very difficult to treat the carbon with the fluorine. Fluorination is difficult task, and any other carbon treatment on the surface is difficult. The fluorine is a little bit studied and is known, and plasma is works very good. So that's the reason we stick into the plasma treatment here with the SF6, and we can see that this packaging material, and we again characterize the different types of the packaging material. Plasma treatment, 5 minutes, 10, 15, 20, 30 minutes, and how we can different treatment, how the fluorine content is increased. You can clearly see that oxygen to fluorine content is keep increasing where we have, this is oxygen to fluorine ratio, and the other elements where we have the fluorine, you can see that 1.3 and also 3.3, and keep, the more you fluorinate, and you more fluorination you get it. But there is a point, you cannot go beyond certain point. We don't want to have more than 50% of carbon is fluorinated, then you will have a trouble. You got all the degraded properties. So there is a fine line between the how much you can fluorinate and how much you can get the final results. So that's the reason we have to be very careful with the fluorination. That's the reason we do different timings to make it which one is the right one. And as long as you keep doing the fluorination, of course, the fluorine is going to be there until complete carbon is gone. But we don't want that to happen. We want to have a carbon right amount, more amount actually. So the fluorination is small amount to make it just a compatibility issues in this kind of situation. And you can see that. So the fluorination treatment, you can see the simple carbon can be highly porous, it becomes. So the porosity is very, very important for carbon for the any filtration applications or any even because surface area increases drastically. That's one of the main aspects of the nanotechnology. When the surface area increases, reactivity increases, and also polymer infiltration increases. So it becomes an integral part of the material, dispersion problems, and all those things will be solved. So we can clearly see that it's happening here, plasma treatment, when you do the fluorination, and also fluorination in the sense is carbon bonding also will be there in the with the fluorine CF bond, it forms some cases that we can clearly see from the spectral analysis. So that's why we did here in this case, and also we try to put it into one of this polymer, polypropylene. Again, this is another polypropylene is another polymer which is extensively used for the automotive application, like a bumper and other kind of stuff. So that's the reason we use this one waste material to make it. And we study all these thermal properties, how does it behave, melting point, and also cross-linking, and the glass resistant temperature, how does it changes by using the neat polymer is the base one, and then we change it all these polymers, how we will the crystallinity increasing, other kind of stuff. So crystallinity has increased drastically from neat 47 to 51, 52. You get a crystallinity percentage is huge. So that's where we can try increasing crystallinity means strength is increasing and all those kind of stuff. So the melting point increases and thermal properties does increase here. You can see that the neat is here where the decomposition temperature and with adding these other polymers, various percentages, it can increase. So that's a huge amount of decomposition increasing. And the 342, we are going up to almost 400. So that most we are getting like a 40 to 60 degrees increasing in the thermal capabilities of the material, which can be used, extended the thermal capabilities can be used for the some engine components of the material where the polymer can be not be used as it is. The neat polymer cannot be used for this. Composite can be used in the application. So that's the reason these simple treatments and the processing, and also again we show almost all of the waste material can be used for these different applications. This is another one where you can see that beneath the mechanical properties, the tensile strength, we see the huge improvement where this Young's modulus or tensile strength is 21, we get up to 41 MPa. So that's a huge, almost 2 times higher than the properties what we can get the need by adding this carbon, huge improvements we can produce. And this is the reason the plasma works very well. So we can get these more information, means the more better properties for various applications. So that's the one. And again, we studied all these properties, not only that, and also we study the microscopic analysis to see whether really polymer infiltration is there and polymer particles agglomeration is there, and how long we can, how much percentage maximum we can add to before they get completely agglomerated and started getting the degraded properties. The more you add, sometimes at a certain point is going to particle-particle interaction. So you don't have a particle and polymer interaction, then you will have a agglomeration and then properties degrade. So the plasma helps in very good in that. So the particle-particle interaction, instead of that, is the particle to polymer interaction. That means if we interact better with the polymer, then you have a very good composite to work with. So that's why we can get this kind of thing. So we do all this microscopic characterization and can clearly see that there is no minimum agglomeration in this kind of situation. The other applications also, again, we said the carbon, this is from the chicken feather carbon. We use the chicken feather carbon as a same procedure here. Again, we take these feathers and clean it, wash it, do it clean process because we do not have any contamination. And if needed, sometimes we do ball mill. Sometimes we don't need it. Directly we can heat it, and then you get the carbon powder from there, and then you plasma treat it, and finally get the material. So we can see this carbon is, you can see some of this lattice structure here, and highly porous, and this is 10 nanometer scale. You can clearly see the carbon produced from the chicken feather is, it looks totally different than the other carbon what we got from previously from the rice or packaging waste and other kind of stuff. So again, simple characterization here. Now we do the FTIR and the Raman spectrum to show the what kind of carbon we have, crystallinity of the carbon, and also different nature of the carbon we can analyze with the Raman spectrometer here. And basically we're observing the G band and D band, the ratios that will tell you the crystallinity of the polymer, amorphous background, or those kind of things. And again, we characterize the SEM analysis to see what kind of chicken feather carbon or plasma treated carbon, what is the difference we have, porosity, and also the different elements. What is the element of component of the nitrogen, oxygen, and carbon. Then we have the chicken feather one has mostly a good amount of carbon there because the feathers is the keratin. You get the nitrogen in that situation, and also the oxygen content. So we analyze these XPS analysis, and also we characterize this material, and also if needed, sometimes we do activate the carbon with the chemical activation. This is done with the KOH, and then again we see the crystalline nature of the carbon to modify. So ultimately, the main idea is to get a different, a very good carbon in the sense highly crystalline, highly porous, those kind of things. So this is the one in the TM. You can clearly see that particles are very, very small, and also they are crystalline. So it is a good amount of material to work with, and that's the reason we use the surface area can be further increased in simple plasma treatment or even the chemical activation. This situation here, I can, as I mentioned to you earlier, as we did the chicken feather, we plasma treated this material again with the KVH plasma treatment or a 5 minutes plasma treatment, 10 minutes plasma treatment. You can see that the KVH chemical treatment is a little bit tedious process, but is comparable. When we do it with the 5 minutes, 10 minutes plasma treatment, does give the similar result. So that's a very good information. We can get it instead of doing the chemical treatment, wasting a lot of chemicals, and the plasma is a clean process. This is a there is no chemicals wasting, and then chemical contamination is not there. The chemical treatment is takes a lot of chemical to be waste. End of the reaction, you will be wasting a lot of chemicals to landfill or throw it somewhere. So in this case, the plasma is not just a powder. You create it and we're done with it. So we don't have any other contamination to the environment here. So this is a clearly showing that the plasma is as good as, even better than the chemical treatment. Here, and these chicken feathers, actually we look at this porous volume, and also we look at the surface area measurements in this one, and the neat one, and the treated one, KOH or plasma treated, and it's a very good activation, and also the plasma treatment ones are as good as the other one, other porosity and other aspects of it. This is the reason we did this one for the supercapacitor device applications. This is for this electronic application. The carbon powder, we get plenty of them. You know that chicken feathers are plenty available. Can get by use for the diversify these kind of application. Instead of, we can always put it into the polymer, get the better polymer applications I showed you earlier. But this can be used even for the supercapacitor application. So like some of these kind of battery applications can be used. So that's why we shown you this experiment here. And this is a when the device, the 3D printed electrode we made, and we studied the capacitor applications, and we show the very good results in this kind of distant thermostatic charging, discharging. Plasma activated device carbon is much better than the simple other KOH carbon. You can see these two are slightly different. So we can have different applications, different source of carbon can be used. So that's why I'm trying to show you here. To go further here, I need to show you a few more examples here on the waste source of carbon. From this, as I mentioned, coffee grinds or waste coffee, coconut shells, and other kind of carbon here. And this is a coffee grind carbon. We've been working quite a bit now, few years now. So we can make this kind of carbon simply by burning and cleaning and those kind of things, and the plasma treatment. This is as it is. We burn carbon, you get a very nice carbon. The reactor will show that, and we can simply get few nanometer of carbon, and it's a really high surface area, and also you can see some of this crystalline material and get the nice structured carbon. So this carbon, we used it in this one of this 3D printed application. So the way we did it is take this carbon, get it from the coffee grind, and then you put it in the epoxy resin system. So again, this epoxy resin, if you don't know, it is in a very aerospace applications they use it. Most of the wing structures or tail or those kind of things, epoxy resins are extensively used. Those high engineering application composites are made carbon fiber based. But here in this case, we try to put this carbon material into the epoxy resin to strengthen the properties, and we actually developed the method to 3D print. So take this epoxy resin system, two of them, part A, part B, we mix it together and the 3D print. And while 3D printing, that those two liquids has to be mixed almost 50-50%. So we try to mix it in the syringe itself and 3D print into the coupon. You can see that here, and this we can see the mechanical properties. And you can see that pure epoxy resin system has a very low mechanical properties, but when we add the carbon, this has a very high mechanical property. So that's a huge improvement you can get by adding small percentages, less than 5% in this case. We add it and you get, and this one also published journal. And also we use this carbon, we treated with oxygen and also the fluorine also, but this is the one you can see that oxygen content is increased drastically by the more you treat the carbon with oxygen, you get the oxygen content. So that will give the more reactivity for the epoxy resin system. When fluorine and ammonia, they're all good for the epoxy resin system because the epoxy based in the mostly amine based resin systems. The curing agent is amine based, and you have a nitrogen, you will get a better addition, better curing, and get the final properties are better in this kind of situation. Again, this is the one where the coffee grind XPS analysis we did with the fluorine. Actually, this is most of the experiments in the XPS we did with collaboration with the UAB. Their UAB, they have a very good XPS. They are part of our Alabama export. Dr. Vora and his group, and also Dr. Paul, they are very helpful here. In this case, I want to thank them because all the XPS data, without that, we don't know what kind of analysis surface modification we are getting it. So this is a very good technique to identify on the surface what we have it. And you can see this is one done in the last week. This coffee grinds, we did the fluorination and the different timings. And you can see the huge amount of fluorination has happened. Fluorine content has increased drastically here 9 to 10% by using different times. This is the one is a 10 minutes and also 15 minutes and also 20 minutes of fluorination. So the more fluorination you do it, you can keep increasing, but after a certain point, it starts degrading. So that's where is the main problem in the sense we need to know the ultimate, what is the maximum we can fluorinate it. We cannot keep doing the fluorination hours together and get more fluorination. Then you end up having only fluorine. It's of no use. So that's where is the main important point. That's the reason we have to do several experiments to find out which is the right amount of the carbon fluorine content we have. Then we can use it for the application. This is a carbon fluorination, and we did the oxygen one, and this is the fluorination one, and we can do ammonia, and we're trying to get together all the results of the ammonia, fluorination, oxygen, how epoxy can be modified. We may getting all these three different properties without changing any of the main ingredients. So we are not changing the polymer material or carbon. We are changing the surface modified carbons to get the varieties of the properties, increasing of the material properties so that you don't have to look for the new polymeric synthesis with the same properties what we have, higher mechanical thermal properties of this kind of material. To show you some of them, actually we have another biomaterials. This is a chicken eggshells. We have been also working for quite a bit here. Calcium carbonate from the chicken eggshell. We have maybe several now close to 10 years. We have a huge amount of materials working on this calcium carbonate with the waste chicken eggshell. You can Google it, you can find out a lot of information on that, and we try to modify them for biomedical application or filler application. In this case, we did this calcium carbonate with chicken eggshell again. Not going to go over everything, but they're here. We get the chicken eggshells and clean it and crush it and get into the ball mill and make into the nano size. Once we are not burning here, we are not burning anything here. We are just in a chemical treatment and just crushing, ball milling, and you get the nano size, or even sometimes use ultrasound to make into the nano size particles. Once you get the nano size particles, we treat it with the oxygen or fluorine to make it to the more compatible for the polymeric material using. So this will show you here. The simple eggshell surface looks like this, and when we treat it with the oxygen, it looks like this, and when we treat with the fluorine, it looks like this. So you can see that all these three different carbons. The carbon is source is the calcium carbonate, the source is same, but the moment you treat with the differently, you get a different porosity, different surface area, and different reactivity. So this is the SF6 one, we have a fluorine. So the fluorine is much easier compatible to the most of the thermoplastic or thermoset polymeric materials, even biocompatible. So it can be used for these kind of applications. And simple oxygen treatment. We are not doing any toxic chemicals there here, but you can see the surface completely modified. So these are the simple techniques it can be only done with the plasma. It's a very simple procedure. Otherwise, it's very difficult to get these kind of treatments and other kind of situations here. Again, this is the characterization. We do it here. Again, to check the fluorine content, if we do the fluorination, we see the fluorine content here can drastically increase. Calcium carbonate doesn't have any fluorine to start with. And when you have the fluorination, you have a huge amount of fluorine. And also, if you're doing an oxidation, you can see the oxidation amount is increased. And also, any element we are looking at, compared to all the elemental analysis, we do it to find out whether we have really done the fluorination, XPS, and also energy dispersive spectroscopy. These two tell us exactly what we have. And compared to studying these two, again, if you go for the microscopic analysis to show you the surface area. On the surface, how does it looks like? And then you can do the surface area measurements. So all these four main experiments will exactly tell you whether we have whether we have any surface treatment or not. So then this one, the one we're trying to do it is here, we're taking this polymer and putting into some thermoplastic polymer to make it to the some of these automotive applications. So the best ways we did is they can make into filaments. Polymer filament. This filament is made with eggshells and also polycarbonate polymer, and we can 3D print. Once we have these filaments, we can 3D print any part, any shape, any size that can be done. And 3D printing is a huge. Once you have a basic lab scale, if you can print it, you can extend it to the industry level to print any material, anything. So for the better application. So this is a 1 to 5% of the calcium carbonate is added treated polymeric materials here. And also, this is some of these other 3D printing biomedical applications. We have been working on it. You take those eggshell, plasma treated one, and infuse into polycaprolactone and make a scaffold. Scaffold material is made with the 3D printing, and this can be used for the many bone grafting or bone regeneration or tissue engineering applications. So we can create a tissue or whatever the way we want the shape and give the skeletal structure, and then we can put it into the cells. The cells can grow and becomes a real part of the material. So that's where all these biomedical applications have been used. So to cells to grow, you have some skeletal scaffold to have adhere to grow that. So we need to show that whether the plasma treatment enhances the cell adhesion. So that's what we're trying to do that one here. And this is the one we 3D printed and show the scaffold fabrication. And also this is another method where we have electrospinning, where we make a fiber, like it's like a cotton candy. So the scaffold is the nano size fibers. You can see that you can like a hair-like material, like cotton, basically. We can spin it. We have a hydroxyapatite or a calcium carbonate from the chicken eggshell, and you take this polymeric material and you get this cotton candy kind of scaffold. And this cotton candy scaffold can be wrapped into or made into any shape, and then we can grow the cells, the live cells, and become the integral part, like bone regeneration application. Because the hydroxyapatite is extensively used for the bone grafting and other kind of applications, because most of our bone made of hydroxyapatite. So that's a biocompatible material. And also we have the same source is also biocompatible. We are not making this one from synthetic sources. This is made from the eggshell or the seashell. So those are the all happens to be biological biomaterials. So that's the reason it's much more easy for any grafting of this kind of application. In the sense, biocompatibility is very high. So to show here, and we treated this polymeric material. This is the stained fibers here, and I don't know whether you can see this are the fibers, and this is the fibers here. And with this a neat fiber, and also we have the neat fiber here. There is no cell. You can see that there is no standing here, blow dots or anything. But where we had it after the 3 days and also 5 days, and you can clearly see that these materials, what's happening is the bone cells. When we put these fibers into the bone cells, and bone cells start growing. So since we have a plasma treatment on these fibers, this is the one actually we take this fiber. This has a hydroxyapatite and the polymeric material. Then we have this caprolactone polymer. This polymer and we made into the fibers, and these fibers match, we put it into the live cells. So when we put it in the live cells, because of the hydroxyapatite and the plasma treatment, and the cells adhere to the cells very good. That means they are thriving and growing bigger. So that's what we need. Once you grow bigger, that's where the growth is happening. And that's where we can clearly see that the plasma treated one is much better. You can see here the growth is there much more in this kind of situation. Again, we tried with the different materials here, 2%. You can see that huge amount of the bone cells are growing. You can see that blue dots are huge amount. We can clearly see where we don't see it in the leaf fiber itself is a very minimum, but it keep growing here. You can see that 5 days one is huge, almost like it become a fully occupied with the cells. We don't see any fibers anymore. All the fibers are consumed and the cells consumed, and then you will have only the bone, the cells are grown. So the cell growth is very good, naturally is growing. So that's a good sign for the any biomedical application. So I think that was the last slide, and I think we are on time here. Looks like 3 minutes we have for the questions, and I would like to thank the students who worked on it. And also I wanted to see if you are interested, you can get all our eggshells or biomaterials research work. And if you can simply Google it, you can find them. Most of the papers are published here. Most of the work is already published in the literature. You can easily find them. This is the students, most of the work is carried out by the students here. Zahiruddin, actually, he's now Dr. Zahiruddin, he recently just graduated, he got a PhD. And Mohammed Idris is a few years old. He's doing a PhD in Drexel. He did some of this waste polymeric materials work. And Shardai Johnson, she completed her master's and she was working on the coffee grinds and other things. Chibu was working on the coconut shell. Alila working on the 3D printing, and Vincent was working on one of the uh, eggshell material, and we have some electronic applications and other things. And financial support, especially the EPSCO, the equipment is all that we bought it from the EPSCO grant, and other grants supported the work we have been working on this one. I think that's the last slide. If you have any questions, I'm more than happy to answer. Thank you very much for your attention.
Thank you so much, Dr. Rengari. At this time, we don't have any questions, but if anyone submits them at a later date, I'll make sure I get them to you. Thanks again for everyone joining us today, and we'll see you at the next speaker series. Bye-bye.
Okay, thank you. We are debating or will be?
We're good.
Okay.